So now when we see the structure of a Fiesel cipher technique, so the plain text will be divided into two halves, left and right. So each side will consist of 32 bits. Then the right side portion will have a round function, that is using key subkey K1 on the right side bit. So round function, what is this? We'll see later or in today's lecture. So after the round function, the output will go to the XOR functionalities. The input, another input will be left half of the portion. So once it is done, these two portions will be swapped. So this is the one round. So similarly, there will be 15 more rounds. Total 16 rounds will be there in this structure. And remember, each round will have same functionality. That is a round function, right? So that was the Fiesel structure. So the DES is based on the Fiesel structure only. Yes, clear, right? The Fiesel structure and what is the key size, block size, etc. So people still joining. Okay, no problem. So what we are going to do, discuss in today's lecture will be what is the history of a DES and the DES encryption. So those are the two objectives in today's lecture. So what is the history means? So how it was developed, right? Or so it is used encryption scheme based on the DES. So most widely used encryption scheme, so which is adopted in 1977. So NIST, so National Institute of Standards and Technology. So initially in 1960s, IBM has set up a research who is led by the Horst Fiesel. So that's why we are calling it as a Fiesel structure. Now he developed an algorithm. So now, at that time it was called as Lucifer, and it works as a blocks only, and each block consists of 64 bits, but the key size was 128 bits. So 128 bit key means so many number of possible keys, 2 power 128, right? So encryption is also somewhat difficult, and the cryptanalysis, so who is trying to attack like a brute force attack, he will try all possible keys. So very it will take years, 1,000 years to decode that ciphertext. But there was some problems in that, but we will see. But after that, there is a refined version of Lucifer, which will be using the key size of only 56 bits to fit in on a single chip. So reducing we can say the structure, or we can say the design, circuit design, so to fit on a single chip. So this redefined version is headed by these two scientists, Walter Tuchman and Carl Mayer. So in 1977, this redefined version of Lucifer was adapted as data encryption standard. So what was the criticism on this is, now, so what was the, the changes made here is in DES or redefined version of Lucifer, the plain text block is 64 only, but the key size will be reduced to 56. So how many combinations we will get? 2 power 56 combinations. So which will be approximately 7 into 10 to the power 16 possible keys. Whereas in Lucifer, the plain text block is 64 only, but the key size was 128. So that means 2 power 128 combination. So there is a drastic change in the possible keys, right? Yes, following? Yes, are you getting my point here? So what was the Lucifer and what is the redefined version? And now we are calling it as a DES. So one, a criticism on the DES was the key size. So there may be possibility of decrypting or decoding, or we can say brute force attack. So what was the brute force attack? Anyone? Please tell me. Yes, anyone knows what is the brute force attack? Please respond. No one knows?
Some kind of hack, sir.
No. See, brute force attack, nothing, I mean, no, like a complex. What are the possible keys are there? Trying each and every possible key. If k is equal to suppose 4, the possible number of keys will be 2 power 4, 16. We can easily try all the different keys. If k is equal to 16, so 2 power 16 keys. As the number of keys are increasing, it is very difficult or impractical for the brute force attack. So it's very difficult to decrypt this ciphertext. But so the criticism was, if k is equal to 128, so brute force attack is not possible, or it may take no years, 1000 years or more than that. So still, in the 56, yes, even one encryption technique is taking 1 microsecond, so it may take 1000 years, 1000 plus years. So still, the brute force attack is impractical in even 56 bits also, the key size. And the second, the criticism was the algorithm, the DES algorithm is actually classified. So there is one concept called SBoxes, substitution boxes. So these boxes were classified. So it is not disclosed to users, etc. So users don't know, or user may think that, so there may be some drawback or something which is, I mean, we may attack, I mean, the opponent may attack based on this information which is there in the S boxes. So as they are classified, so users don't know, is it really vulnerable to any type of attack. So that was one more criticism on the DES. So on the S boxes, okay, one is S boxes and the one was the key, number of keys. So those are the two, I can say, the criticism on the DES. So but still the DES algorithm was used. Initially it was used for cash dispensing systems, right? So later all the classified information is encrypted using the DES algorithms. So after that there may be one advanced versions of DES, advanced encryption standard, then triple DES, right? So those we are going to discuss also. So I hope the history is clear, how it is evolved. So now we will see the DES encryption. So what are the steps, what is the block diagram, etc. Yes, following. So we need to be careful here. So there is a big block diagram and I will try to explain each block, what is happening. Yes, are you with me? Please respond.
Yes, sir.
Yes, sir.
So the DES algorithm or encryption technique will have the plain text blocks. So the plain text and the key to be encrypted on the key. So it is a two inputs, plain text and the key, and the plain text must be 64 bits. Remember, in DES encryption, each block size or the plain text block size is 64 and the key is 56 bits. So 2 power 56 possible keys. So very large amount of keys, right? So around 10 to the power 16 or 17 possible keys. Now, what is happening in the DES encryption? How the plain text will be converted into ciphertext. So it will have 3 phases. So what is happening phase 1, phase 2, phase 3, I will explain, then we will see the block diagram. So in phase 1, the plain text block will be passed through one initial permutation. So remember, in phase 1, the plain text passes through a block which is called an initial permutation. Initial permutation. So we will denote by IP. So what is the permutation? Tell me. So it's just rearranging the bits only. That's it. See, when we take suppose 4 bits, 1010. Suppose this is the plain text. I'm just taking example of 4 bits only, but actually it will be 64 bits. So 64 bits means, so there is 64 factorial combinations or sequences possible, right? So by rearranging these bits, I may get one sequence something like this. I may get one more sequence something like this. Yes or no? So that will be performed in the first phase. Yes, clear? So the plain text passes through an initial permutation which rearranges the bits, in plain text. This output we will call it as a permuted output. Okay. Permuted output. So is this clear? So initial phase is very simple. It will take 64 bit and it will be passed through one block which is called initial permutation. Initial permutation or permutation is nothing but rearranging the bits. That's it. Clear? All of you?
Yes, sir.
Right. So in the phase 2, what happens? This permuted output will pass through, or in this phase, it consists of 16 rounds. So the phase 2 is nothing but the feature structure only. So the data which is coming from the first phase or the permuted output will pass through these 16 rounds to produce we can say pre-output. So what is happening? Just see here. So in this phase, it consists of 16 rounds with the same function. Remember, with the same function. So round function will be same, but only variations will be keys. So 16 rounds with the same function. So function is nothing but like something like this. Permutations and substitutions only. It will perform substitutions and permutations. We will see that what is happening, the substitutions and permutation. So same functions, other functionality is nothing but substitution and permutations only. So with the different keys, how many keys? 16. 16 rounds means 16 keys. So with the different keys. So once the 16 rounds are over, see carefully. So there will be left and right halves, correct? So these will be swapped to produce pre-output. So what is happening in the second phase is, so there are 16 rounds with the same functionality. That functionality is nothing but substitutions and permutations with a different keys. Once the rounds are completed, remember, before phase 3, left and right halves must be swapped to produce we will call it as a pre-output. Clear up to this? Please confirm. Clear? Please respond. All of you, is it clear?
Yes, sir.
Right. So what is the phase 3? It's very simple. We have performed initial permutation. So we will perform opposite operation, which will be called as inverse initial permutation. So here what is happening is the pre-output will pass through a permutation so which is called as inverse initial permutation. So inverse initial permutation we will denote by IP inverse, which produces 64-bit ciphertext, which produces 64-bit ciphertext. Right? So very simple. The output coming from the after the 16 round and the swapping, after the swapping, that output or pre-output will pass through again the permutation, but this is denoted by IP inverse, inverse initial permutation. So here it will produce the 64-bit ciphertext. So plain text again 64-bit. So initial permutation, then 16 rounds. So before it is going to the last phase, we have to swap left and right halves. Then finally inverse permutation, so which is producing the 64-bit ciphertext. I hope all the points are clear. Now see the block diagram, you will get some more information. See here. So the left side 64-bit plain text it is taking, so it is performing the initial permutation. So 64 bits will be rearranges. How, we will see later. Now, so there will be 16 rounds. For these 16 rounds, the subkeys will be coming from the right side. We will call it as a key generation. So here, how it is generating, that we will see, few minutes later. After round 16C, there is a 32-bit swap. So left and right halves will be swapped. Then finally, what happens? Inverse initial permutation. So see. So inverse initial permutation, so which is providing 64-bit ciphertext. So now what is happening here? So this is phase 1. This is phase 2 and this is phase 3. Clear, all of you? Phase 1 initial permutation, then phase 2 16 rounds with same functionalities but different subkeys. Before it is passing through inverse initial permutation, so there is a swap, then final ciphertext. Now we will try to see what is happening in the key generation. So this we can say is a key generation or subkey generation. So initially the capital K will be 64-bit only, but in there is a operation which will be called as permuted choice 1. So in this we will eliminate 8 bits. How? That also we will see now. So we will eliminate the 8 bits. So that is a permuted choice 1 which will generating 56 bits. After that we have to perform left circular shift. So we will see in detail later also, just see now, just block diagram wise. So 56 bits will be performing the left circular shift, and after performing the left circular shift, those bits will be going for the next key generation or K2, right? But what is happening to this left circular shift will be again going to the permitted choice 2. So here again permitted choice 2 will convert 56 bits to 48 bits only. How? That also we'll see. So this 48 bits is the K1. Similarly, K2. So based on the round, so there may be 1 bit rotation or 2 bit rotations. That we will see. That also will be the table based on the rounds. So for each round, left circular shift, permitted choice 2. Left circular shift, permitted choice 2, which will generate the subkey K2, which is 48 bits, remember. So again, what will be there in these rounds, we will see. Is there any question? Don't worry about the permitted choice 1, 2, left circular shift, what is happening in the round. Just see as a block diagram what is happening. So right side is a key generation, left side the phases of the encryption. Now we will see in detail what is happening in the rounds. Yes, clear? Please respond.
Yes, sir.
Yeah. So now the details of the single round. Now see, right side is the key generation, left side is the round function. Now what is happening? I'll explain. So I'll take one more. I will show all the tables later. So there is a 64-bit K, right? I told you. So when I arrange 1, 2, 3, suppose 8, 9, 10, and so on. How many? 8. If I make 8 by 8 matrix, last bit will be 64. Correct? So in the permitted choice 1, generally what they have done is this 8. I mean 1, 9. So how many? 8 by 8. 1 second. Yeah. No, not this. Yeah. See here. Are you seeing this table? So 8, 16, 24, 32, 40, 48, 56, 64. These bits will be eliminated. As I have written like this. So all these bits will be eliminated. So 8 bits are eliminated from the 64. The output will be 56. Okay?
Yes, sir.
So that is what is happening in the that permitted choice 1. So here. So permitted choice 1, the 8 bits are eliminated. Clear?
Yes, sir.
Now after that, once we got 56 bits, these 56 bits again converted into 2 halves, 28 bits, 28 bits. Okay? See, the encryption technique is nothing but performing substitutions and permutations so many times, right? So that the different keys, different permutations, so it's very, very difficult to cryptanalyze or decoding or decrypting the message. So when there is 28 bits, for these 28 bits we will perform the left circular shift. And again for these 28 bits we will perform left circular shift. Different, see. Then we will combine. Again we will get 56 bits. So that is how. Now what is the left circular shift? Everyone knows. Suppose 1 0 1 0 1 1 etc. So what is the left circular shift? 1 bit left circular shift means this 1 bit will come back in the first bit, correct? Like this. 0 1 0 1 1 1. So that is one left circular shift. If I perform 2 times, this 0 also will come here. So 1 0 1 1 0. So those number of bits will be there. So only rearranging again we can say, or circularly shifting. So many times it will perform. So based on the rounds, 1 time, or one bit will be rotated, 2 times or 2 bits will be rotated. So that table also I will give. Is this clear? So that is what is there here. So Ci minus 1, Di minus 1. For the next stage, after left circular shift, these bits are going. See, Ci minus 1, the next stage, after left circular shift, they are going to the next stage to generate K2 or Ki plus 1, etc. So once shifting is done, then again there is a permitted choice 2. So those, the positions will be different. Again, we will take the different combinations, different sequence in the permitted choice 2. Clear? Up to here. So which will generate the Ki. If I is equal to 1, K0. Sorry, K1. If I is equal to 2, K2, etc. etc. So this is the key generation. Is this clear to all of you? Yeah, this is the key generation. So this is the input key. Eliminated. So only 56 bits. Again, once that is done, permitted choice 1. See here. So once I eliminated, I did not take as it is like this. No. I have taken some different sequence. See? Actually, it should be 1, 2, 3, 4, 5, 6, 7. But the 57th bit is coming in place of first bit. 49th bit is coming in place of second bit and so on. Now you may ask, how can I remember this? Yes or no? No need to remember.
Yes.
It's a random. See, I can generate my own sequence. You can generate your own sequence, etc. But it will be based on, it may take so much time to going through all these permuted choices or permutations. But it's an example we can say, right? So no need to remember anything. The sequences are permutations. Clear? All of you?
Yes, sir.
In a permitted choices, the K, actually it is happening 2 operations. So first one is 64 to 56 is not a permitted choice. So when I make this 56 random sequence, then that is called this entire operation will be called as a permitted choice 1, random sequence. Clear? Huh? So not only eliminating these 8 bits, rearranging these remaining bits is called permitted choice 1. All of you getting mine?
So మనం random గా ఎట్లాగా arrange చేసుకోవచ్చు సార్? ఇక్కడ ఏ నంబర్ తను?
అదే. See, I'm having 56 bits. Okay? Suppose
Yes, sir.
4 bits అనుకుందాం.
Okay, sir.
So 0 zeros నుంచి 4 1 వరకు different sequences కదా? Yes, correct? So we will write the code actually. See, this is we are writing a code to generate random sequences. It will not generate like this. No, it's a not matrix. Actually, we should consider 57, 49, 41, etc., last 4 as a one row. So it is not, easy to write as a row. So they have written in the matrix form. So randomness is in our hand. So there is 4 bits means 4 factorial combinations are there. 4 factorial combinations. Yes. So 0, 0, 0. So 0, this many combinations. Then 1 combinations, 2 combinations. So many combinations will get. So for 56 bit, 56 factorial means any number, any sequence we can take. So that should be random. So that we will write in a algorithm or in a code using Java, using C++, whatever. Getting the point? Please confirm. Is it clear?
I have one doubt.
Yeah, please.
In permitted choice, when 64 is changed to 56.
Correct.
కంబుల్ చేసినప్పుడు మనకి మోర్ నంబర్స్ ఎలా వచ్చాయి సార్?
యా క్లియర్ గా లేదు, కొంచెం క్లియర్ గా చెప్పు.
నథింగ్ సార్, నథింగ్. డౌట్ ఏం లేదు. క్లియర్ అయిపోయింది.
వాయిస్ క్లారిటీ లేదు.
డౌట్ క్లియర్ అయింది సార్.
ఓకేనా? అంటే ఏంటి, ఐ మీన్ ఎనీ హౌ వి ఆర్ ఎలిమినేటింగ్ దిస్ ఆర్ డిఫరెంట్?
క్లియర్ సార్, అది కాదు, డౌట్ క్లియర్ అయిపోయింది.
Okay, done. All of you, is it clear? So it is not like we need to remember, it's a random. So I mean we can follow one different techniques. For these 2 bits we can have two I mean number 2 difference, number 3 difference, number 4 difference, etc. We can generate the sequence, right? Getting the point here? So that's why the structure of the algorithm is not disclosed. The DES algorithm structure is not disclosed. So or we can say classified. So that's why the user don't know which permitted choices or which blocks or which substitutions or permutations are used. Is it clear? Please confirm. Yes or no?
Yes, sir.
Clear kada? See, that's why I mean I told or not. So this DES or AES you can do on project. So I mean it may take so much time to rearranging, taking the permutations, but once you're done, so that will become a project. Now in permitted choice 2, what is happening? Just rearranging. See, once I perform the left circular shift for this 56 bits, 28 bits separate, 28 bits separate, then it's a random sequence we can take, that is called as a permitted choice 2. See how many columns? 3 plus 8 columns and 6 rows. 3, 8. So 8 by 6. So it will be 48 bits. Okay. So again, so there may be a reduction of 8 bits. Correct? Yes or no?
Yes sir.
Yeah. So this is the permitted choice 1, and after permitted choice 2 we got only 48 bits as a K1. Now see how many bits are rotated. For round number 1 only 1 bit rotated, round number 2 only 1 bit rotated, but round number 3 to 8 2 bits are rotated. Then round number 9 1 bit. Next 10 to 15 2 bits are rotated to generate different possible number of keys or so many variations to get that. So there is a different number of bits are rotated based on the rounds, either 1 bit or 2 bits. Clear this one also? How many number of bits are rotated in each round? Yes, clear? So we have come up to here. So 64 to 56, then left shift, then permitted choice 2 we will convert 56 to 48 bits only, and after the left shift those bits will go to the next stage to generate again one more key. So when we come to the round function, see what is happening. So again 2 halves. See, before converting these 2 halves, it is already gone through initial permutation, remember? Clear? So before we are converting into left and right half of the plain text, it should be performed initial permutation IP. Then Li minus 1, we have to go for the XOR, but for the XOR, the right side portion and the K bit will come. Now see here, different functionalities will come. So one is, this is only 32 bits, right side portion, but the input, the other input for the K or the key is coming only 48 bits. So first we have to perform the expansion from 32-bit, 48-bit. Expansion table is there. So it's very simple. Suppose A, B, C, D is there. We can add some more extra alphabets, no? We can add E, F, G, H, or we can add Z or X, Y, Z, etc. So just adding the bits. So once expansion is done, so it will become 48 bits. Then in the round function also, there is a one more XOR functionality for this 48-bit key and the right side expansion bits. Then, so the output of the R side should be 32 only. So these two functionalities will convert 48 bits to 32 bits. So that is called SBox, substitution box. So I will explain the substitution box here. See carefully. So right side 32 bits are coming. So using expansion, I'm converting into 48 bits. Then after XOR operation, this KI, which is having 48 bits, the output will be 48, but I need only 32 bits. So what we are doing is, we are converting these 48 bits into 6 bits groups. How many we need? S1, S2, S8, correct? 6 bits each, 6 bits each. 8 6 is 48. We know one operation, how so many number of inputs, less number of outputs. We will call it as a encoder or decoder. Please tell me. More number of outputs, sorry, more number of inputs, less number of outputs. Encoder, right? Yes or no?
Yes.
But not as a, I mean, here it's not an encoder operation. So here 6 inputs, we will get 4 outputs. 4 outputs. So 8 4s, 32. So these SBoxes will perform, it will take 6 inputs and it will produce 4 outputs based on some condition. So that condition also I will explain. Once it is converted into 32 bits, again there is a one more permutation. See here, once we are converted into 48 to 32 using SBoxes, again we will take one more permutation. Again means rearranging the bits. So that will come as an input for the XOR operation. So that output will be transferred to right side and the Ri minus 1 is directly transferred to the left side. So that is the feasible structure only. So Li is Ri minus 1. Ri means Li minus 1 XOR with the function of Ri minus 1 and K. But inside this is the functionality. Expansion, one more XOR operation, then SBox and a permutation. So 1, 2, 3, 4 operations or functionalities will be there in the round function. Expansion, XOR, substitution and permutation. So that I will explain, see, by using tables. So this is the initial permutation. 64 bits will be rearranged. So that means first bit is replaced by 50th bit, second bit is replaced by 50th bit. So 8 by 8. So total 64. So similarly, inverse initial permutation. So after going through so many permutations, etc. So the last round, the first bit will be replaced by 40th bit, second bit is replaced by 8th bit, etc. etc. So this is the just example. Initial permutation will be like this. Inverse initial permutation will be like this. Clear? Please confirm so that I will move forward. Yes or no?
Yes, sir.
Right. Now see what is the functionality of round. So 32 bits expansion, then XOR operation, then SBoxes. Now I will explain what is this SBox is doing. See carefully. So this is the substitution box. So in this, okay, not like this. So suppose this is the SBox. There will be 15 columns, 1, 2, and 4 rows. So 0, 1, 2, 3, 0, 1, and so on, 15. This is only one box. Like this, we will have 8 boxes. Now, for this, each, so there may be a number. It may be 1, it may be 15, it may be 4, it may be 2, 3, 6, 0, no. 8, 9, 11, 5, 7, etc. Maximum number will be 15 only. 1, 2, 3, etc. Any number will be there. So now, for suppose for the SBox, the inputs are how many? 6. So I will denote by X0, X1, X2, X3, X4, X5. Okay. Now, what is the operation here will be? See carefully. The first bit and the last bit will represent a row. So X0, X5 will represent or denote a row. The remaining bits X1, X2, X3, X4 will represent a column. Okay. Now, when we say one example, 1, 0, 1, 0, 1, 0. Okay, this is an example. So 1, 0, the X0 and X5 will be 1, 0. 1, 0 means what is the number? 2. So it will representing the row 2. Then 0, 1, 0, 1. What is the 0, 1, 0, 1 means? 5. So it is representing column 5. So row 2 and column 5. So whatever is there in this box, suppose in this box there is a 10. So 10 number will be converted into 4 binary bits. So 10, 10 is the binary equivalent. So all these numbers will be in a decimal format, or we can say hexadecimal format. That number will be converted into binary sequence, which will provide 4 bits. So this is the SBox operation. Is this clear? I will show the boxes and see what is happening. Understood? So 6 bits, first and last bit will represent a row, remaining bits will represent a column. So for that particular row and column, whatever the number is there, that number will be converted into binary bits. Please confirm, is it clear? Yes or no? Now see the SBoxes. As I told, the criticism was this: in these SBoxes only, these SBoxes are classified. So if I see the SBox 1, see 15 columns, 4 rows. Now see, what is the maximum number you are seeing here in these boxes? Maximum number. It is not more than 15. See, 15. So there may be number of, 15 maybe multiple times will be there, 12 multiple times, etc. If you see any box, any SBox, the maximum number will be 15 only. Okay? Any box. So the reason is, I can, okay, 0 is also there, okay? So from 0 to 15, if there is a decimal or hexadecimal, we can represent by 4 bits, correct? So
Yes, sir.
they are rearranged, our numbers, different numbers they have taken. Once the inputs are coming from the SBoxes, so represent based on the column and the row, suppose 1, 0, 1, 1, 0, 1. Okay. So these are the input for the SBox 1. So 1 1 means 3. So third row. Then 0 1 1 0 means 6. 6 means 0 1 2 3 4 5 6. So that means we have to take this number and this 1 will be converted into 0001. So that will be SBox 1 output, 4 bits. So similarly, SBox 2 maybe different number, then it may select suppose 12. So 12 means 1 1 1 0 0. So that is SBox 2 output. Similarly, here we may get 0011, etc., etc. So we'll have total 8 SBoxes. So each SBox output is 4 bits. S1 4 bit, S2 4 bit, etc. Total output will be 32 bits. Okay. So again, how to make these SBoxes? So again, it will be based on the algorithm. Yes, we can make our own also, but it will take a lot of time. So they have taken 3-4 years. So yes, but we know some examples. So from that you can generate your own SBoxes also. So that will become a project. See why I'm telling all this means you can choose AES or DES as your mini project or major project. So SBoxes, up to SBoxes are clear. Next, I think yeah, expansion. See here, expansion. 32 bits from the right side, Ri-1 will perform. I mean, go through expansion permutation box or a functionality. So see here, 1 to 32. So here we are adding some extra bits. So there may be repetitions also. See, 8, 8, 9, 9, etc. So based on some repetitions, so we can expand. Just adding some extra bits. Now, after the SBoxes, if I see the block diagram, after the SBox output, again there is a permutation. So permutation is nothing but taking the random sequence. So that is this example. I mean, permutation functionality. See, 1, 2, 3, 4, 5, 6, 7, 8. 4 by 8. So total number of bits will be 32. The expansion, then XOR operation, then SBox, then this permutation, which will generate 32 bits. So how are numbers written in SBox? Yeah, so that is also the classified one. So the numbers that we have to choose as a random are some logic, right? So that is the one criticism on this DES algorithm. The SBoxes are classified. So we don't know really they are doing a good functionality or not. Really they are secure or not. Really they are vulnerable to any type of attack or not. Right? Again, yes, I cannot say how they have written like this. But we can return our own also based on some logic. I can make my own logic to generate the SBoxes, and those SBoxes will be will not be disclosed to anybody, because once they know, they can easily decrypt the messages. All of you, is it clear how the SBoxes are written? So that will be based on their logic. We can go with our logic, right? But remember, we have to go multiple operations, and the operations must be unique. So I cannot go all the numbers same, right? So there should be some uniqueness when we are writing the tables, when we are going for the permutations, when we are going for the sequences, when we are going for the expansions. So which will generate a message which will have more security. The ciphertext should not be decrypted by anybody who is if he is taking One day, then there is nothing is there in the encryption. So no need to encrypt that message. So one is taking so much time to decrypt. So that is a very good encrypted message. Yes, clear to all of you? All the functionalities, permutations. I hope all the points are clear. So that is the encryption. So and see the block diagram. If you are having any question, you can ask. So this block functionality will be same for all rounds, but only change will be this ki, because so many times left shifts is happening. So obviously it will generate different key, right? But whatever is there in this function, same. Only here changes will be SBox for each S, right? So yeah, for each round the SBox is also same. No change in the SBoxes. Once SBoxes are fixed, those SBoxes will be fixed for each round. Only change is the ki. I hope all the blocks operations are clear. Okay. So what is that decryption? Once I finish this, so it will be over. So decryption is nothing but just inverse operation. But the first round key will be 16. See, LD not is equal to RE16 means, so LD decryption left side, which will come from RE16. Encryption right side 16 will come LD not. But first round key will be 16, second round will be K15 and so on. Same operation, inverse, but the number of, key is the only variable here. So first round is K16, then 15 and so on. Everything will be similar to the encryption only. Clear? All of you? I hope all the points are clear. Please try to revise. I will share the PPT. If you are having any question, we can discuss in tomorrow's lecture. In tomorrow's lecture, I will I will discuss some strength of the DES. Then I will start AES also, if possible. So strength of DES. What are the strength of DES? Or drawback? Then we will start the advanced encryption standard also. Okay, so that's it for today. Thank you. I'll take the attendance from the Zoom only. You can leave, you can attend for the next lecture.
Thank you, sir.
Yeah.